Started. Okay, so welcome back everyone. Thank you all for coming. And so before we get started, let me say that today we are using the microphones in the room. So please be aware of that. You will be heard on Zoom and will be recorded. So just so you know. And otherwise, for online participants, if you have questions, please type them in the chat or unmute yourself and we'll be monitoring that. So without further ado, let me introduce our first speaker, Melissa Sherman-Bennett, who will tell us about the M=2 amplituhedron, hypersimplex, and cluster algebras.
Yeah, so thanks so much for the opportunity to speak from across the Atlantic. I'll be talking about some joint work with Matteo Parisi and Williams, which is up on the archive, so you can find all the details there. And just a warning, I do have the chat visible, so if you put something in there, I will probably see it right away. So if you have questions for the end of the talk, please keep them. Okay, so let me get started. So, right, I'll be talking about two mathematical objects, actually one more than the other. Really, I'll be focusing on the M=2 amplituhedron, which fits into this like calculating scattering amplitudes project that was discussed on Monday. And then I'll be talking about its mysterious connection to another object, the hypersimplex, which people are probably more familiar with. And then, of course, I'm going to be talking about the connection to cluster algebras sometime in there. Okay, so before I define either the amplituhedron or the hypersimplex, I need to talk about the totally non-negative Grassmannian, which I'm going to use in the definitions of both of those objects. And okay, this has already come up in the conference and I think people are pretty familiar with it. So I'm just gonna basically set some notation to go through this quickly. Okay, so I'm fixing two integers, k less than n. I have some pretty standard combinatorial notation here. And GRKN for me is the real Grassmannian of k-dimensional subspaces in R to the n. And I think about the Grassmannian with respect to its Fluker embedding. So I've got Fluker coordinates hanging around, indexed by k element subsets of 1 through n. Okay, so I'll be interested in this special, particularly nice subset of the Grassmannian called the totally non-negative Grassmannian, TNN Grassmannian for short, introduced independently by Lustig and then later and in very different language by Postnikov. I'll be using Postnikov's definition. So, okay, as people probably know, the TNN Grassmannian is just the set of all elements of the Grassmannian with non-negative Fluker coordinates. So exactly what you think. And the thing that we perhaps like best about the Grassmannian is that it comes kind of automatically with a stratification according to which Fluker coordinates are positive and which ones are 0. And this stratification turns out to be incredibly nice. Okay, so just to set some notation, so pick M, a collection of k element subsets of n, and the stratum SM is all of those elements of the TNN Grassmannian where the Fluker coordinate pi is positive if and only if I was in my collection M. So M is exactly recording which Fluker coordinates are positive and all the other ones must be 0. Okay, and if you choose M unluckily, of course, then the stratum will be empty, but that's okay, we ignore the empty ones. If the stratum is non-empty, M is called a positroid of type Kn. This word came up yesterday. It's a portmanteau of positive and matroid. And the type Kn thing is just because we're in GRKN. And we call this stratum, Sm, a positroid cell. And this word cell here is not an accident. These actually are homeomorphic to open balls. And this is part of the extreme niceness of this decomposition. Okay, and maybe of more kind of even more interesting to this audience maybe is it was suspected for quite a long time, but follows from fairly recent results of Galoshin and Lamb, that each one of these positroid cells is actually the positive part of a cluster variety. So for the biggest positroid cell, that's the totally positive Grassmannian, where all Fluker coordinates are positive. Of course, that cell is the positive part of the cluster variety, which is like the whole Grassmannian, or maybe the Grassmannian take away some divisors if you want to do that. But also all of the smaller ones are positive parts of cluster varieties. These are the the open positroid varieties of Knudsen-Lehmann-Speyer. But kind of for this talk, all I want to do is emphasize this fact. Okay, and kind of by definition, of course, like I said, so the TNN Grassmannian, it decomposes into a disjoint union of these positroid cells. And this decomposition is actually topologically incredibly nice. It's a cell decomposition, even better, it's a CW complex, even better, it's a regular CW complex. That last result is due to Galosh, Lam, and Karp. Many other people contributed along the way. And so, yeah, this is just kind of, it's an incredibly nice decomposition. And the thing I want you to take away from this slide is we have this space, the TNN Grassmannian. It decomposes in an incredibly nice way into positive parts of cluster varieties. And there's only actually one decomposition this way that we know of. So to get the amplituhedron and the hypersimplex, what I'm going to do is take this very nice space with this nice decomposition, and I'm going to hit it with a couple of maps and kind of see what happens. So let me talk about the amplituhedron first. So this was defined by Nima Arkani-Hamed, who spoke on Monday, and Jaroslav Trnka. And the idea behind the amplituhedron is its volume, or I don't mean volume at all, but I mean something like volume, is a scattering amplitude. So computing a scattering amplitude should be the same as computing the volume of this amplituhedron. So how is it defined? Well, first, I need to pick a helper matrix Z. If you're a physicist, Z is going to encode the data of the particles moving around, but for me, it's just going to be a matrix. It will be n by k plus 2, and it should have positive maximal minors. Okay, so this matrix Z induces a map Z tilde from the totally non-negative Grassmannian to some other Grassmannian. And this map is just induced by matrix multiplication. So if I have some element of the TNN Grassmannian A, it gets mapped to the element of GRK k plus 2, represented by the matrix A times Z. And the amplituhedron is just the image of the TNN Grassmannian under this map. This is my notation for m equals 2 amplituhedron. Okay, so I will be interested in not just the image of the whole TNN Grassmannian under Z tilde, but also the image of each positroid cell. So I'm going to call the images of positroid cells Grasstopes. So ZM is the Z tilde image of the closure of the positroid cell SM. And I'm actually going to, so I'm not going to care about all Grasstopes here. Instead, I'm going to care about some special ones. Before I tell you about those, I need to tell you, I should tell you some more things about the amplituhedron, I realized. So one thing to say is, despite the hedron suffix, the amplituhedron is not usually a polytope. It's something else. And it's 2K dimensional, that is its full dimensional inside of its ambient Grassmannian. And also the Grasstope here, that's also kind of a lie. The Grasstopes are not usually polytopes, they're something else. Okay, so the ones that the Grasstopes we're going to care about particularly are called positroid tiles. And these are basically the largest Grasstopes on which Z tilde was really well behaved. So we call a Grasstope a positroid tile if it's full dimensional, so 2K dimensional, and Z tilde was injective on the positroid cell that the Grasstope came from. So these are the Grasstopes that are, in some sense, they're very close to positroid cells. Z tilde isn't like squishing them at all. Okay, and we will be particularly interested in a decomposition of the amplituhedron into these positroid tiles. So I'm going to call this a positroid tiling. And so this is a collection of tiles with disjoint interiors whose union is the whole amplituhedron. Okay, so why do I care about these two things? Well, the motivation is still from physics. So I said that very roughly, like, the volume of the amplituhedron is a scattering amplitude. But the problem is the amplituhedron is large and complicated. Its volume is difficult to compute. But the volumes of these positroid tiles is computable. And so, okay, we've got a big complicated thing whose volume we don't know, and then smaller full dimensional pieces of it whose volumes we do know. So of course, like, the reasonable thing to do is to look at precisely this kind of decomposition. So a decomposition of the big space into the smaller pieces whose volumes we know. But in that decomposition, okay, you want it to, you want the small pieces to cover the whole thing, and you don't want the small pieces to overlap in their interiors. Okay, so that's one half of the story. And so I'll say what this work is we classify the positroid tiles of the amplituhedron, and we also, in some sense, give a characterization of the positroid tilings. But before I tell you about those things, I need to tell you about the hypersimplex. Okay, so this is possibly the meanest way to talk about the hypersimplex in the world. It's kind of like the least comprehensible thing I could have chosen, but I'm doing it for sake of analogy. So if you already know about the hypersimplex, good, this will look kind of weird. And if you don't, I'm sorry, I should be giving you a different definition, but oh well. Okay, so what is the hypersimplex? Okay, so for me, okay, so basically on this slide, what's going to happen is I'm going to define all the same things as I defined on the last slide, but I'm going to use a different map. So instead of using the Z tilde map, I'm going to use the classical moment map on the Grassmannian mu. Okay, exactly what this map is doesn't actually matter too much for the talk, so I'll just say it's a map. I'm going to think about it as a map from the TNN Grassmannian k+1n to r to the n. And the image of the TNN Grassmannian under the moment map is called the hypersimplex, delta k+1n. Okay, and there's a picture of this of delta 2,4 here. It's the big octahedron. And okay, so what I should tell you is that this is a polytope. On this slide, we're dealing with polytopes, and it's n-1 dimensional. And there's a much nicer description. In fact, it's the convex hull of the torus fixed points of the Grassmannian, but that's okay. And you want to think about it this way for now. Okay, and again, okay, so I want to be thinking about the images of positroid cells under this map. So when you apply the moment map to a positroid cell closure, what you get is a polytope called a positroid polytope. I'm going to denote those with a gamma. And in green here is a positroid polytope sitting inside of the hypersimplex. Okay, and again, we're going to care particularly about those positroid polytopes that are kind of closest to the positroid cells that they came from. So those are the positroid tiles. And these, so again, they're going to be exactly the full dimensional positroid polytopes where mu was injective on the positroid cell. So exactly the same definition as the last slide, except I've swapped out the word grasstope for positroid polytope, and I've swapped out the Z tilde and mu. Okay, and then again, I can think about decompositions of my large space, delta kn, k+1n, into these smaller nice pieces, and I'm going to call that a positroid tiling. So just like the last slide, this is a collection of positroid tiles with disjoint interiors which cover the whole space. Okay, so part of why I made all of these definitions was in exact analogy to the last slide, because I'm going to make a bigger analogy later. But the objects on this page are also kind of intrinsically of mathematical interest. So these positroid tiles, if you know about matroid polytopes, it turns out that these are exactly the matroid polytopes of series parallel matroids, which have kind of shown up before in they have special significance in the Dressian in terms of tropical linear spaces. And these positroid tilings, okay, so this is actually kind of an odd notion from the perspective of like polyhedral geometry, because it's some decomposition of the hypersimplex where I'm not saying anything about how the boundaries of the large pieces intersect. So it's a looser notion than a polyhedral subdivision, but that's okay. It includes a lot of polyhedral subdivisions. And the polyhedral subdivisions, which are positroid tilings, they correspond to maximal cones in the positive Dressian, which is equal to the positive Grassmannian. So yeah, this is, I don't know, it's a nice space which cluster algebra people should care about, the positive tropical Grassmannian. And it was recently studied from this perspective by Spire and Williams and Arkani-Hamed Lam and Spradlin. So yeah, there's some sort of like secret cluster relevance in these things already. Okay, so I defined these two notions of positroid tile, one for the hypersimplex, one for the amplituhedron, two notions of positroid tiling, and I'm going to tell you about the relationship between them. But first, let me orient you a little and give you some examples of m=2 amplituhedra. So before our results, basically there's only a couple of parameter values where we have a good understanding of what's going on with the amplituhedra. The first is when this Z matrix is square. In that situation, the Z tilde map is an isomorphism. And so you get that the amplituhedron is just isomorphic to a TNN Grassmannian. And in that situation, there's only one positroid tile, so the tilings are really boring. For the other parameter value for which we know what's going on before our results is for k=1. In that situation, the amplituhedron is actually just a polygon. That's the only time it's a polytope. For k=1, it's a polygon sitting in the projective plane. And the positroid tiles there are just the triangles on 3 vertices of this polygon. So the tilings are exactly the same as normal triangulations of a polygon. And what do we know about okay, so outside of those two cases, I cannot give you, before our results, a nice intrinsic description of the amplituhedron or any positroid tiles just as subsets of GRK k+2. I can only give you the definition involving Z tilde, or I can only give you the description involving Z tilde. Yeah. And what do we know about tilings in general? Well, Bao and He give a recursion to provide tilings of the amplituhedron, but it won't give you all of them. And it also, well, you don't have any kind of global understanding. You only have a recursive understanding of tilings. Okay, so with that said, let me now tell you, well, about what we know now. So what are the results of this paper? So first, we show each positroid tile for the amplituhedron is in fact the positive part of a cluster variety. So each one of these small pieces we're interested in decomposing the amplituhedron into just the positive part of a cluster variety. So this is some cluster variety, which I'll tell you specifically inside of GRK k+2. And what this does is, well, it gives us a really nice description for the positroid tile, right? It's just cut out by some cluster variables being positive. So having that very concrete description of each positroid tile, as you can imagine, it helps you prove things. So we also say more. So we prove a couple of very curious conjectures, conjectured by Lukowski, Parisi, and Williams. So first we show that the positroid tiles for the amplituhedron are in bijection with the positroid tiles for the hypersimplex. So kind of the good behavior of the Z tilde map and the good behavior of the mu map, they're somehow that happens in this, like in the same situations. And I'm going to denote this bijection with a hat. So if Zm is a positroid tile for the amplituhedron, then gamma m hat is the corresponding positroid tile for the hypersimplex. Okay, and moreover, so not only do we have this bijection between positroid tiles, but this induces a bijection between the positroid tilings. So a collection of positroid tiles is a positroid tiling of the amplituhedron for all Z, if and only if the corresponding collection of positroid tiles for the hypersimplex is a positroid tiling of the hypersimplex. Okay, so what I want you to take away from this slide is that the amplituhedron has many decompositions into positive parts of cluster varieties. But so it's not, so in the TNN Grassmannian case, for example, we just have one decomposition. So now we've got many, but the situation is not too bad because what this many is, well, combinatorially speaking, it's governed by something polyhedral, which as a combinatorialist, it feels like I can understand polyhedral things. So this many is governed by the combinatorics of something polyhedral. And what do I mean there? Well, this result tells me that the positroid tilings of the amplituhedron, combinatorially speaking, they're the same as the positroid tilings of the hypersimplex. And on the hypersimplex side, the positroid tiles are just polytopes. And so I'm just decomposing a polytope into some other polytopes. Yeah, so my kind of the thing I want you to take away is, okay, we've got kind of the same nice phenomenon as in the TNN Grassmannian. It's a little bit more complicated, but it's somehow manageably more complicated because we have something polyhedral in the background. Okay, so let me tell you now a bit more. So I'm actually not really going to say, I don't have time to say anything else about this result. So let me just tell you about the cluster varieties that we see. So what I'm going to do is I'm going to start with a properly bicolored subdivision of an n-gon with area k. So it's a picture that looks like this. The area thing is just telling me how many subpolygons I've colored black, basically. So I'm going to start with one of these pictures, and I'm going to associate it to a cluster variety. And the positive part of that cluster variety will be one of these positroid tiles, and that will give all of them. So if you see, okay, so I'm going to tell you now, what I'm going to do is basically kind of in terms of cluster structure, it's exactly the same as normal like the normal triangulations of polygons pictures. It's just I'm only going to pay attention to the black polygons here. So I'm just going to ignore the white ones. So what that means is I'm going to have exactly one seed torus for each triangulation of the black polygons of my properly bicolored subdivision. Okay, so right, and so to give you the functions on this seed torus, I need to define some new functions on the Grassmannian called twistor coordinates, and those will be my cluster variables. Okay, so let me give you twistor coordinates really quickly. So y is some element of the Grassmannian, grkk plus 2, and let zi denote the ith row of z. I'm going to define a new function, a twistor coordinate yij, which is just the determinant of the matrix where I put y on the top, and then zi, so the ith row of z, and then the jth row of z. Okay, and this is a square matrix because y is k by k plus 2. So this determinant is just, you know, it's fine, I can just take it. So these twistor coordinates, they're linear in the Plücker coordinates of y. And these will be my cluster variables, more or less. And I should also say, we didn't pull these out of nowhere. Twistor coordinates have featured before in amplituhedron literature, namely a conjecture of Arkani-Hamed Thomas Trnka, who gave a conjectural description of the amplituhedron as a subset of grkk plus 2 in terms of these twistor coordinates. And this is one of the things we managed to prove. So I'm just going to flash it on the screen and then come back to it a little bit later. Okay, so now let me tell you about the let me tell you about the seeds for these cluster varieties that we define. So, okay, so I'm going to think about the cluster variety associated to a particular subdivision, bicolored subdivision of the n-gon with area k. So let me fix this one. And I'm going to tell you how to get a seed from a triangulation of the black polygons of this subdivision. Okay, so first, I need to choose one special boundary arc of each black polygon. Now, it doesn't really matter which one you pick, but I'm going to ignore this arc from now on. Okay, and then, okay, I want to talk about a seed, so I need to pick a triangulation. Let me pick this one. I hope the blue is visible. I chose the arc from, I added the arc from 1 to 4. Okay, so how do I get a seed from this? Well, the quiver is going to be the usual kind of triangulation quiver, but I'm only going to pay attention to arcs which touch a black triangle. and I'm going to ignore in my quiver the special boundary arcs, but everything else is exactly the same as the usual triangulations picture. So let me just draw the quiver quickly. Okay, so that's the quiver I get. So in particular, I have a vertex of my quiver sitting on top of each arc of a black triangle of this triangulation. Okay, so what about the cluster variables? Okay, so let me focus on a particular arc of a black triangle, let's say 1 to 4. So what's the cluster variable I associate to that arc? Well, it's going to be a ratio of 2 twistor coordinates with some sign. So first, just the twistor coordinates. The one on top is the twistor coordinate kind of corresponding to the arc I'm sitting on. So here it's going to be y14. And then the one on bottom is the twistor coordinate corresponding to the special arc of whatever polygon my arc is sitting in. So this 1 to 4 sits inside of this quadrilateral, and my special arc here is 1, 2. So in the bottom of this ratio, I should put y12. Okay, and then I have some signs. And the sign is -1 to the area from I to j. Okay, what is this area statistic? It's really easy. All I do is I count the number of black triangles that are to the left of the arc I to j. So in this case, 1 to 4. Okay, so here, my arc that I'm paying attention to is 1 to 4. I see exactly one black triangle to its left. And so that means I should have a 1 in the exponent here. And then I have the same kind of sign in the denominator, but now I'm using the area from A to B. So, okay, so A to B is 1 to 2. How many black triangles do I see to the left of that arc? None. So I should see a 0 in the exponent there. Okay, and those are my cluster variables. So it's just this ratio of twistor coordinates with some sign in the front. All right, and so the cluster variety in question here. Okay, so I on the previous slide I give you a single seed, so a single seed torus. And it was corresponded to a triangulation of the black polygons of my subdivision. And the cluster variety in question is just the union of all the seed tori where I vary over all triangulations of my black polygons. Okay, and the point is that the positroid tile is exactly the positive part of this cluster variety. And if I vary over all possible bicolored subdivisions, I obtain all positroid tiles. And okay, so this is a nice thing to say, but let me also write down kind of exactly the concrete description that we get for each positroid tile. So it looks like this. Your positroid tile is just the subset of the Grassmannian where the certain twistor coordinates, the ones corresponding to arcs of black triangles, they have a specified sign. That's it. Okay, so we have this nice description. It's very concrete. It's also very combinatorial, where you have a nice kind of combinatorial object in the background, which is giving you all of the information here. And so with this, we can prove the conjecture of Arkani-Hamed Thomas and Trnka on what the amplituhedron actually looks like inside of GRK K+2. And I should mention, they prove one direction of this equality, and what we do is we prove the other. Okay, so let me just quickly go through this. What is this description? Well, it is that the amplituhedron is the closure of those elements of the Grassmannian where some twistor coordinates are positive and a particular sequence of twistor coordinates has exactly k sign changes. All right, and that's what the amplituhedron is. Okay, and as threatened, so that was the result on positroid tilings. As threatened, I'm not really going to say anything about the relationship to the hypersimplex. I'm just going to flash the theorem again on the screen that we end up getting a bijection between positroid tiles of the two spaces, and then also a bijection of positroid tilings of the two spaces. Here's a little picture. So here are the two positroid tilings of delta 2, 4. So each one of the differently colored highlighted bits is a positroid tile. And here are the two positroid tilings of the relevant amplituhedron A412. And the bijection is given by colors. So this blue positroid tile over here corresponds to this blue positroid tile over here, and you can see that if I take the positroid tiles in this tiling and look at their corresponding tiles over here, I get a tiling over there. Okay, and the only thing I'm going to say about this is, well, how do we prove this? Well, we start out knowing that there's a bijection between tiles. So what we do is we take the simultaneous refinement of all positroid tilings on both sides. So we split up each space into even smaller pieces, and then we kind of cross our fingers and hope that those smaller pieces are also in bijection. And it turns out this is sort of true. It's like not quite true, but it's true enough for us to prove the theorem. Okay, and I'll stop there. Thanks so much for listening.
Any questions for Melissa, either in the room or in the chat? Oh, yes.
Does this tell us, does this give us any hints about what's going on for the m=4 amplituhedron?
That's a really good question. So I think, well, yeah, so Lauren, Matteo, and I are currently thinking about some m=4 things. The track we're currently taking is to think about the momentum amplituhedron, the appropriate momentum amplituhedron in that case, which is kind of, it's not quite just two copies of the m=2 amplituhedron, it's like two copies of the m=2 amplituhedron that have been sort of glued together or something, or there's some like twisting going on. The idea there being, oh, our m=2 understanding is so good now, maybe we can also understand this like slightly more complicated thing kind of built out of m=2 amplituhedra. The conjecture is that if you're talking about m=4, you shouldn't be looking at the hypersimplex. Instead, you should be looking at this momentum amplituhedron as kind of the dual object. Yeah, so I can't tell you anything concrete, but we're like sort of hopeful.
Cool, thank you.
Questions? Maybe I have a question. So in the beginning, you talked about the volume. So does this let you compute the volume of this amplituhedron then?
Yeah, so I think from the perspective of, yeah, so first I should say, so the m=2 case is kind of a toy case. If you want to get something physically relevant, you need to be dealing with m=4 because space-time is 4-dimensional. Okay, fine. For the purposes of computing volume, just to compute the volume, all you need is one positroid tiling. You don't really need to understand all of them. So in some sense, the volume question is kind of over as soon as you have this recursion to obtain at least one tiling. But it's also possible that maybe some of the tilings that we have like discovered are, maybe it's like they're easier to deal with than the ones that come from this recursion. I'm actually not sure. So yeah, I would say possibly you don't need our results to compute any volumes, but maybe the computation gets easier with them.
Okay. There's one more question. Thank you.
Okay.
Does this tell us anything about the differential form on the amplituhedron? Because my understanding is that you can get it from push forward from any decomposition. So each of those decompositions gives you the differential form, and conjecturally everybody believes you get the same form regardless of the decomposition. But is that the kind of thing? Could you check that now?
Oh, probably. I mean, the trick, I guess, would be to associate something in the differential form to a piece of the hypersimplex instead, and then try to argue things on the hypersimplex side, which I don't know, maybe that's more doable. I'm not sure. I mean, yeah, I'm not sure what it would translate to on the hypersimplex side, but yeah, it seems reasonable that it would shed more light on that question. None of the people in the project are people who think about the differential form, so we have not really thought about this. It's definitely a good question.
Questions? Doesn't seem to be the case. Okay, so let's thank Melissa again.